Okay, this video is going to cover some of the basics of a standing wave and the way the math of it adds up. It will be broken into a few parts and try to cover one concept at a time. So first of all, a standing wave is a wave in which there is a reflection, some kind of echo or reflection from a fixed end, in which causes the wave to change its phase, essentially flip upside down, if you will, when it hits that reflection point. That sends an interference pattern back and forth through the wave, which causes some parts of the wave to add their energies together and thus have maximum displacements, and other parts of the string, snakey, whatever material it is, to have places where the interference causes destructive interference, which means they has very little motion at all, if any at all, and we call that a node. So if you look at an actual device like a rope, a string, or a spring that's made up of different coils, at its rest position it would be just a straight line across. Now once we start this interference pattern, we're going to get places where the medium appears to be stationary, and those are called nodes. The energy at that point essentially is being canceled by the reflection energy. At the same time, we're going to get points where the displacement is maximum, and they're going to be the opposite of nodes, so we call those antinodes. And that's going to be areas where the energy is actually working together to create a large amplitude. So in our picture of some basic standing waves down here, this area right here would be the rest position. This is where the string or slinky, whatever it is, would be. When we set up the reflection pattern, we get points here where there seems to be almost no motion at all. And those are called nodes. Then we also get points where the interference pattern actually adds together, and we get this large up and large down. The sections where we get the most up and down, those are going to be called antinodes. So over here on this one, you can see we actually have 1, 2, 3, 4, 5 of the antinodes, and then we have 1, 2, 3, 4, 5, 6 of the nodes. And you can see that there's one more segment to that particular one. That indicates that we have a wave that is happening more often, or a higher frequency. So what we want to do is try to see exactly how this pattern sets up. So we're going to look at this quick simulation. I just have a material like a slinky that's attached, fixed here by this clamp, so this end cannot move. So there's a little green part here, this one particle cannot move. I'm just going to send a pulse down the wave. It just means one disturbance. We watch it travel down. Notice that should notice a couple of things. First, it's if you watch any individual particle, it's not the particles that move along, it's the energy of the wave that moves along. The second thing you should notice, we'll do a quick restart here and do a pulse again, when it hits the fixed end. So here it is before it hits the fixed end. The disturbance is above the rest area. Boom, after it hits the fixed end, in reflecting and bouncing off of that, the wave energy has gotten flipped upside down. Now if you combine a upward wave and a downward wave in a series of these pulses, a train of waves, then when they add together, you'll get your antinode. When they are canceling each other out, you'll get your node, which is where essentially no motion is going to take place. So that's what's the reason it's happening, is that idea of interference. Okay, now again, we can count the nodes and antinodes from any kind of shape. The nodes are real simple. Just look for the rest position. They're going to be the ones that stay on the rest position. And then your antinodes, again, are you going to be places where you get the maximum up and down displacement. Now keep in mind, the string or slinky or whatever is either going to look like this, or it'll look like this, or it'll be something in between. It's not that the string is in two places at once, but that's the places between which it bounces back and forth. So each individual particle is going back and forth. Now, in this case, in the picture on the page up and down, this kind of a picture, recognize that not every particle on the wave has the same overall amplitude. Okay, so this one here has a smaller amplitude than this one over here does. And of course the node has essentially zero amplitude. So in a standing wave, different particles will have different amounts of amplitude. On the right-hand one, again, antinodes, upper section, place width maximum 1, 2, 3, 4, 5, 6. So I get 6 antinodes over here. We'll get 2 antinodes over here. In terms of trying to figure out, in terms of the effect on the wavelength, the distance between two nodes, so from here to here, on this one from here to here, if you look at the overall shape of a cycle, it would actually go all the way over here. So the distance between two nodes is equal to 1/2 of the wavelength lambda. So if you're trying to determine the overall wavelength of a standing wave, it's going to essentially be double the number of, or twice the length in terms of the number of nodes. Be careful about counting antinodes. You don't count the antinodes twice. So the antinode is either the up part or the down part. There's not 1, 2, 3, 4, 5, 6, 7, 8 antinodes here. There's 4 antinodes, up and down sections. Okay, so we're going to use that idea to start looking at different harmonics and calculate the wavelengths, etc., as we go ahead.